This is section 5.4.2, Irrational Numbers, adding and subtracting square roots and rationalizing the denominator. First, we're going to talk about adding and subtracting square roots. Square roots with the same radicand can be added or subtracted by adding or subtracting their coefficients. Now you'll remember that the radicand is the number under the square root symbol. For example, if you have the square root of 4, 4 is the radicand. If the square roots do not have the same radicand, simplify each radicand to attain a common radicand. If the radicands do not simplify to a common radicand, then the square roots cannot be added or subtracted. Now below you can see some examples of adding and subtracting square roots with like radicands. Now there are no numbers in these examples, but they basically are the definition of adding and subtracting square roots. So in our first example, we can see that both of these square roots have radicands of c. There's the radicand c, there's the radicand c. Since they have like radicands, we can add the coefficients together. The coefficients are the numbers out in front of the square root symbol. So in this case, we can add a plus b and keep the square root of c. Very much like having a common denominator with fractions, we keep the common radicand. If it's a subtraction problem, the process is the same. We have the common radicands, so we can subtract our coefficients, a and b. So we end up with a minus b, and we keep the common radicand, the square root of c. All right, let's look at some real examples with numbers. So our first example is 7 square roots of 2 plus 5 square roots of 2. As you can see, we have the common radicand, the square root of 2, in both cases. So all we need to do is add our coefficients together. So in this case, we add 7 plus 5, we get 12, and we keep our common radicand, the square root of 2. Second example, 3 square roots of 2 plus the square root of 8. This is our first example where we do not have the same radicand. So what we have to do is simplify these radicals to see if we can get a common radicand. Well, let's start with 3 square roots of 2. The square root of 2 cannot be simplified. So 3 square roots of 2 has to stay 3 square roots of 2. Now let's look at the square root of 8. Does 8 have any factors that are perfect squares? The answer is yes, 4. We can rewrite 8 as 4 times 2. And of course, we can take the square root of 4, which is 2. The other 2 stays under the square root because we cannot take the square root of 2. Now, as you can see, we have the common radicands, square root of 2 and square root of 2. So we're ready to add our coefficients. 3 plus 2 is 5, and we keep the common radicand of the square root of 2. Now let's look at our third example. Obviously the most difficult. We have 2 square roots of 72 plus 3 square roots of 50 minus the square root of 128. You can see that none of the radicands are the same. So we have to simplify each of these in hopes of getting them to be the same. So let's start with 2 square roots of 72. 72. What perfect square goes into 72? Well, 36 times 2 is 72. And 36 is a perfect square. We can take the square root of 36 and get 6. We leave the other 2 under the square root symbol. 2 times 6 is 12. We end up with 12 square roots of 2. Now let's simplify 3 square roots of 50. What perfect square goes into 50? 25. So we have 3 times the square root of 25 times 2. We can take the square root of 25. It is 5. We leave the 2 under the square root symbol. 3 times 5 is 15. So we have 15 square roots of 2. This is looking good because so far both of these terms have a radicand of the square root of 2. Now we're ready to simplify 128. So the question is, what perfect square goes into 128? Well, 128 is a pretty big number. I know 4 is a perfect square, and I know 4 goes into 12 3 times, and it goes into 8 twice. So I know 128 can be written as 4 times 32. We can take the square root of 4 and get 2. The 32 stays under the square root symbol. However, 32 also has a perfect square in it because 16 times 2 is 32. So we can rewrite this as 16 times 2. Since 16 is a perfect square, we can take the square root of it, and we end up getting 4. 2 times 4 is 8. The square root of 128 simplifies to 8 square roots of 2. Now, let's rewrite our problem. We have 12 square roots of 2 plus 15 square roots of 2 minus 8 square roots of 2. Each of these terms has a common radicand, so we can add and subtract the coefficients. 12 plus 15 is 27. 27 minus 8 is 19. We keep the common radicand. 19 square roots of 2 is our answer. Alright, next we're going to talk about rationalizing the denominator. If the denominator contains a square root, multiply the numerator and denominator by the denominator and simplify. Let's look at some examples. First example is 15 divided by the square root of 6. Since there is a square root in the denominator, we need to rationalize the denominator. We do this by multiplying both the numerator and the denominator by whatever the denominator is. In this case, the square root of 6. Now you'll recognize that we're really just multiplying by a fancy form of the number 1, because the square root of 6 over the square root of 6 is 1. In math, we're always allowed to multiply by the number 1 because it is the multiplicative identity. Alright, let's continue. Now we're multiplying fractions. 15 times the square root of 6 is 15 square roots of 6. The square root of 6 times the square root of 6 is the square root of 36. The square root of 36 it is a perfect square, so we can take the square root of 36 and get 6. 15 over 6, we can treat this as a fraction that can be reduced. 3 goes into 15 and 3 goes into 6. So 3 goes into 15 5 times, 3 goes into 6 twice. The square root of 6 cannot be simplified because it does not have any factors that are perfect squares. So our final answer is 5 square roots of 6 over 2. Let's look at our second example. 3 square roots of 2 over the square root of 5. Since there is a square root in the denominator, we are going to rationalize the denominator by multiplying the numerator and the denominator by the square root of 5. Now we're multiplying square roots in the numerator. 3 times 1, that's the coefficient there, is 3. And the square root of 2 times the square root of 5 is the square root of 10. In the bottom, we have the square root of 5 times the square root of 5, which is the square root of 25. Now, of course, the square root of 25 is a perfect square, so we can take the square root and get 5. Now we need to ask ourselves, can the square root of 10 be simplified? There are no perfect squares that are factors of 10, so in this case, it cannot be simplified, and 3 square roots of 10 over 5 is our final answer. Let's look at our final example. Once again, we see the square root in the denominator, so we're going to rationalize the denominator. We're going to multiply the numerator and the denominator by the denominator. So in this case, we're going to multiply by 3 square roots of 8 over 3 square roots of 8. Multiplying the numerator, we multiply 7 times 3 and get 21 square roots of 8. In the denominator, 3 times 3 is 9. The square root of 8 times the square root of 8 is the square root of 64. The square root of 64 can be simplified to 8, so that's 9 times 8. We know 9 times 8 is 72, so we have 21 square roots of 8 over 72. And now we need to ask ourselves, can this be simplified? Well, let's start with the square root of 8. Can the square root of 8 be simplified? The answer is yes, because 4 is a perfect square and it's a factor of 8. So we have 21, the square root of 4 times 2 is 8, over 72. Now the square root of 4 is 2, so we have 21 times 2 times the square root of 2, all over 72. 21 times 2 is 42. 42 square roots of 2 over 72. Finally, we need to reduce the fraction 42 over 72. We know that 2 goes into both of those. 2 goes into 42 21 times, and 2 goes into 72 36 times. Don't forget the square root of 2 in the numerator. Now, can 21 over 36 be reduced even further? The answer is yes, because 3 goes into 21 7 times, and 3 goes into 36 12 times. Finally, we have rationalized the denominator, 7 square roots of 2 over 12. This has been section 5.4.2, Irrational Numbers, adding and subtracting square roots and rationalizing the denominator.